So linear algebra. One of the keywords here is linear. Everything we're going to do will be linear. Now, we'll do some things that occasionally that have some polynomials involved in them, but you can solve. But what we'll be looking for will be something that we can do using linear systems of equations. So some of the stuff in the middle kind of gets a little fuzzy, but in general, most everything we're going to be doing, or a lot of it, is going to be solving linear systems of equations. Let's see if I can stretch this mic cord out longer, just in case I need it over here to hear better. So hopefully we all know that for something to be linear, that just means that we have terms in which our variable is just to the first power. If you have a variable squared, then it's not linear. If you have, essentially, if you have a term where the degree is not 1, then it's not linear. If we had that, while x itself and y itself have exponents of 1, remember the degree of a term is a combination of all the variable exponents. So actually the degree of that term would be 2, so that's not linear. So typically when we have a system of equations, we'll have more than one equation. So that's an example of a linear system of equations. We could have more equations than that. In the past, all systems of equations that we've done, we would generally have the exact same number of equations as we had variables. And we'll get into this class more on, well, how many equations do we need for a certain number of variables? What does it mean if we have more equations? What does it mean if we have less? Also, typically, the notation we've used for systems of equations, if we had two variables, we would use like x and y, or a and b, or m and n, or something like that. Often in linear algebra, instead of using two different letters, you might use the same letter, but you'll use different subscripts to differentiate between different variables. So x1 and x2 are actually two separate values. So in this system of equations, let's just change this to 4. We have two variables, and we would be looking for, well, which particular value for x1 and which particular value for x2 works for both equations. So that's the next point. Just a reminder, what does it mean to be a solution of a system of equations? So a solution is an ordered pair, or if we have 3 variables, an ordered triple that works for every equation. If it just works for one equation but not the others, it's not a solution. If it doesn't work for any of them, of course, it's not a solution. But if an ordered pair, ordered triple, however many variables works for all equations, then it's a solution. So let's just do this one real quickly. One technique we've used in the past, we did elimination. Notice notice if we were to add these two equations together, the x2's would cancel, so 2x1's equals 12. Divide both sides by 2, and we get that the first unknown is 6. And then we can back substitute to get the other unknown. We can substitute that 6 into either of these equations. So I'll just take the top one. So if we replace x1 with what we now know it to be, subtract 6 from both sides. So our other unknown is 2. So we probably recognize that 6 plus 2 is 8, 6 minus 2 is 4. So yeah, that ordered pair is a solution to this system of equations because it works for both equations. Ready to take a test on that, and that'd be nice just for that to be test point. Let me pull up the book instead of writing all of these out. I'll show you a few things. So we're using WebAssign. And actually, the book that I have a hard copy of is the last edition. We're using the 7th edition. We talked about that. We talked about what linear equations are. Right here, the top, we have two systems of equations. And actually, these two systems of equations are equivalent systems of equations. And when we say that they are equivalent systems of equations, we mean that you can attain that system from that one. And in the last problem we did, and things we would have done in, say, Math 112, if we have 3 equations and 3 unknowns, we begin by trying to eliminate one variable and getting it down to 2 equations and 2 unknowns. And then we eliminate another variable and get it down to 1 equation that has 1 unknown, and we can solve that for it. For example, if we take the first 2 equations and add them together, notice we could eliminate the x's. If we add those together, we get y. If we add no z's and 3 z's, we get 3 z's. Add those together, we get 5. So that's where that second equation came from. That third equation, if you got another equation of y and z, did a combination, you could get that last one. So we'll talk in a minute about what things are permissible steps. But basically, if you can multiply an equation by a constant, that's an okay operation. It's okay to take 2 equations and swap them. You can take the first and the second row and swap them if you ever need to. That's permissible, so I guess let's go ahead and write that out. We can swap rows. okay to multiply a row by a constant. Because if you think about it, if we've got some equation, if we just multiply both sides of that equation by a constant, for example, if we multiply both sides by 3, we've changed what that equation looks like, but isn't that equation equivalent to that one? As long as we did the same operation on both sides of the equation, they're the same. So yeah, so if we multiply a row by a constant, then that's okay. And also we can add a multiple of one row to another row, and that's okay. And we'll work one out here in a minute, just to illustrate each of these, or at least some of them. So, an example of doing that, if I had x plus y equals 5, and then I had minus 2x plus 3y equals, let me think of some numbers that would work here. Yeah. When we do elimination in like 112 or 100 or even sometimes an 098, notice just adding the equations straight together, nothing cancels. But if we were to double that top row, and then add that to the second row, as long as I'm adding the left sides together and the right sides together, we still have something that's balanced. So, yeah, notice. Oh yeah, I can't multiply. Thank you. So basically, since that side and that 5 are the same, if I add equivalent things to each side of an equation, we're still balanced. So when we add those together, our resulting equation is still equivalent. That's still an equivalent statement for our system. So what we illustrated there was adding a multiple of one row to another row. So that's still equivalent in our system. Basically, it hasn't changed what our answers are. It just put our system of equations into something that was more easily solved. Notice here we have one variable, so we can divide both sides by 5 and get one of those values. So all three of those are permissible operations. And when we solve these, what we're going to do is we're going to try to get our equations initially to look like this. On the right side there, that's in what is called row echelon form. Row echelon. And the benefit of putting a system of equations in row echelon form is, notice in this example, we know what z is. So once we know one of our values, we can work backwards to get the other values. Okay, we know z, so if we replace that z with a 2, then we could solve and find y. What would that make y? Negative 1. Now that we know z and y, we can plug those values in and we can find x. So row echelon, we have this value. We take that one, we plug it into the previous equation to get that unknown. Now we know both of those, so we plug into there to get our last one. So that's the benefit of putting things in this thing called row echelon form. Now they list let's see. They describe, I think I saw this earlier. Okay, I guess they save that for another section. We'll describe later specifically what we mean by row echelon, but in general, this is it, where you have a stair step, working your way like that. So let's work a problem.
So row echelon, is that just like, I mean, one equation you solve by substitution, but it's just like given. But you don't have to perform any operations on z equals 2. It's just given.
Right. Yeah. And it'll make more sense when we change these into matrices. But that's basically what you're after when you put things in row echelon form. You'll try to get what we're going to call later a pivot in each row. And if you have any rows that have all zeros in them, then we're going to put those at the bottom. So we'll go into a little bit more detail about what it is later. But you're exactly right, basically. We want, if possible, we want to have one variable given, what the value is. And then in the step above it, maybe that variable with one other one, so we can find that one. And above that, those two with one more. Or it could be that the one above it still only has two variables. We might still have, I'm just going to make some numbers up here. So that would be your row echelon form. Notice a progression. At the bottom, we only have one value. And let's introduce this term, pivot. If we think about this top equation as having no y's, this bottom or second equation of having no x's, and the bottom equation having no x's, no y's, basically the pivot in a row or an equation is the first non-zero term. So notice the bottom pivot is here, and then the next pivot is in the previous column, and then the next pivot is in the previous column from there. So in general, that's what we're after when we put things in row echelon Like we're not going to have X as a pivot in two different rows or Y as a pivot in two different rows. We're going to have separate pivots in each row. So that's a pivot, and that's a pivot. Again, that's kind of getting a little bit ahead of what we're going to talk about in this section, but that's kind of a glimpse of what we'll do in the next section. In the next section, basically we get rid of all the letters and just deal with the coefficients and the numbers. Because the letters really aren't, the numbers are what make things cancel out. Like if I have a 2x and a minus 2x, those cancel. Well, the 2 and the minus 2 are what make them cancel. The x is just your variable. So as we get into matrices in the next section, we'll just get rid of the letters altogether. Let's see. They give us a problem where they say use back substitution to solve the system. So let's look at 2x1 minus 4x2 equals 6. 3x2 equals 9. So notice that last equation, we can solve for x2 by dividing by 3. So if we list this as an ordered pair, x2 would be 3. Now that we know what x2 is, we can back substitute into the top equation to find x1. So add 12 to both sides. Divide both sides by 2. So we get x1 to be 9. So that's one of the first things I asked us to do. And we did one example of that already. Back substitute. Now let's take a system of equation that's not already in row echelon form. Let's put it in row echelon form so that hopefully we can get to a point where we can back substitute. So let's see. I mean, I guess I can make well, let's do one that has 3 variables. Let's see if I can find one that's not too terribly awful. Let's do 3x of 1 minus 2x of 2 plus 4x of 3 equals 1. X of 1 plus x of 2 minus 2x of 3 equals 3. And then 2x of 1 minus 3x sub 2 plus 6x sub 3 equals 8. One of the hardest things for me to do on these is to copy the problem down. So the process that we're going to use to put this in row echelon form is called Gauss elimination. Gauss elimination. And Gauss elimination takes what we've done in the past with regular elimination, and it just kind of structures it in a way that helps us to get things in row echelon form. And one thing that we like to do with Gauss elimination is, to begin with, if any of our leading variables, so in this case x of 1, if any of those have a coefficient of 1, we would like to put that as the top equation. So let's start by swapping those two equations. And it's a good idea to make a note each time you do something. We'll do this more when we get into matrices. That first step we did is we basically swapped row 1 and row 2. Now after we have that first pivot with a 1 in it at the top, we're going to do our third allowable step of adding a multiple of one row to another. We're going to use that to get zeros in both of those. So we want to get zeros in both of these positions. So let's see. Let's copy this over. Okay. Copy it. So to get a 0 here, let's take 3 times, let's see, let's think about this real quickly. If this is a 3, what's the opposite of that? Minus 3. So the reason we wanted a 1x1 there is, what's the easiest number to multiply by? Actually, there are two numbers that are easy to multiply by, 0 and 1. So if I want to cancel this 3 out, if I multiply that top row by negative 3 and add it to that second row, then I would have a negative 3 in the top spot, a positive 3 in the bottom spot. So for the first one, I'm going to write that out. So if I multiply the top equation by negative 3, I get negative 3x1 minus 3x2 plus 6x3 equals negative 9. Then that second row is already positive 3 minus 2, positive 4, and 1. So if we were to add those two equations together, our x1's cancel, and we get minus 5x of 2 plus 10x of 3 equals negative 8. So our second row becomes minus 5x of 2, 10x of 3, negative 8. All right. Now if we want to get rid of this 2x of 1, what do we want to do? Yeah, we would want to do that top row times negative 2. We do negative 2 times the top row plus that third row. That'll give us negative 2x of 1 minus 2x of 2 plus 4x of 3 equals minus 6. And then our bottom row was 2x1 minus 3x of 2, 6x of 3. Okay. And a quick note, the benefit of writing those out is, notice we're not really doing any complicated algebra. There's just a lot of arithmetic going on here, and there's so much of it that it's easy to make a small mistake somewhere. So if you get to the end and you're like, these numbers don't look right or they don't work, or I put my extra leva sign and it says it's wrong, then you can go back through each step and see, well, did I really do minus 2r1 plus r3 to get my new third row? And it's easy to miss a sign, to forget to do the right side like I did earlier, or something like that. So when we add these together, those cancel. We get minus 5x of 2, 10x of 3 equals 2. Before we do anything else, anybody notice a problem? Is it completely the same? What's the same? The left side's the same, but the right side's not. What do you think that tells us about the solution? Not 0. There'll be no solution. Because if we think about it, is it possible for us to plug an ordered pair in and do this to it and get negative 8, then take that same ordered pair, do the same thing to it, and then get 2? No, that's not possible. So that brings up, yeah, sometimes we get no solutions. Now, in case we didn't pick up on that, let's work this down a little farther into row echelon and see what it would look like when we got to the end. And I'm going to realign this board real quickly. It's off over there. All right. So this is not completely necessary, but it would be nice if we had a 1 right there in that pivot. So how would I get a 1 right there? What could I do to that equation to make that coefficient a 1? Yeah, by negative 5. Yeah. So basically, if we take that equation, divide by negative 5, or multiply by negative 1/5, then it makes that second equation have a 1 in that front spot. So we still have, where'd you go? We still have that top equation. The second equation will become x of 2 minus 2x of 3. Negative times negative will be positive 8/5. And then that I guess we didn't do this, but what we did there was we did negative 1/5 times row 2, and that gave us the new row 2. So that's how we got that new row 2. Alright, so let me copy this over. Alright, so we want to get, we have a pivot in the first column, we have a pivot there. So now let's get a 0 underneath there. So we have, going back to Gauss elimination, we got everything underneath there zeros. So we got a 1x of 1, and then we made all the other x of 1s go away. Then we got a 1x of 2 in the next row, and we want to make what's underneath it go away. So at the end, we want to have x of 1, some other stuff, nothing underneath that x of 1. We want to have x of 2, maybe something else, and then x of 3. So nothing underneath that x of 1, nothing underneath that x of 2. So notice those are basically diagonal. So how would we get, what could we do to make that go away? Right, multiply the second one by 5. So do 5 times row 2 plus row 3. And that'll give us the new row 3. So let's put this one down. So we're leaving the first row the same. We're going to leave the second row the same. And then we're going to do 5 times the second row plus the third row to give us our new third row. So if we do 5 times the second row, that gives us 5x of 2 plus the third row minus 5x of 2. So how many x of 2s is that? 0. Then we're going to do this to the column of x of 3s. We're going to do 5 times that, so negative 10 plus that, positive 10, so that's 0. So basically, we have a 0 on the left. We didn't have any x of 1s here. When we did 5 times that plus the next one, those canceled. When we did 5 times that plus the bottom one, those cancel. Now if we apply that to these, if we do 5 times, come over on the side, 5 times the top one plus the bottom one, we get what, 10? And anytime we come up with a statement like that bottom one, that's not possible. So in solving a system, if we come up with a false statement as one of our equations, that tells us there's no solution. There's not a single point that works for all 3 of those equations. quick little refresher, there's basically three things that could happen. We could get one solution, and the first two or three problems we looked at had one solution. We could get no solution, and we'll get no solution when we come up with a false statement in part of our row echelon form, where we have, generally it'll be a 0 on one side, a number on the other side, which is not true. Or we could have infinite solutions. Now, infinite solutions, let me just remind you, does not mean that every ordered pair works. For example, that's not what I was trying to do. Try that again. This system has infinite solutions. But that doesn't mean every ordered pair works. For example, does the ordered pair 3, 4 work? If I plug a 3 in for x, a 4 in for y, is that true? No. If I plug a 0 and a 0 in, obviously that's not true. So remember, infinite solutions doesn't mean that every ordered pair will work. If we were to just glance at this real quickly, if you notice, if we were to multiply that bottom equation by -1, we would get that same equation. So infinite solutions means that any ordered pair that works for one equation will also work for the other. Now if we didn't recognize right off the bat that those were opposites, let's try to put this in row echelon form. So we have a 1 in our first pivot. Let's get a 0 underneath it. So how can I get that to be 0? If this has a 1, how can I get that to be 0? By either swapping the rows, multiplying that one, and when we multiply, we don't multiply by 0. We can multiply by any number other than 0. Or adding a multiple of a row to another row.
A lot of you use that.
Yeah. So we can change that second row to the sum of those rows. So our first row, we're going to leave the same. If we add those two rows together, those cancel, give us 0 x's. Those cancel, give us 0 y's. So basically we have 0 on the left. If we add the right sides together, what do we get? 0. So we reduce that system. And is that bottom statement a false statement or a true statement? It's true. So that tells us that if we come out with an equation like that, that tells us there are infinite solutions. Now the way that we describe this, for example, in Math 112, we would say that the solution set is all ordered pairs x, y, such that when we add x plus y, we get 5. Basically, we would list one of those equations, and that would be the solution set. So any ordered pair that works for that equation works for both equations. So there are an infinite number of solutions here because think think about a line has an infinite number of points, but it's not just any point, it's any point that's on that line. Now, in linear algebra, we handle writing the solution set a little differently for many reasons, mainly because often we don't necessarily have just two variables and different kind of weird things can happen. So if we think in terms of pivots, we have X as a pivot, but we don't have a row that has Y as a pivot. And a lot of books refer to a variable that doesn't occur in a pivot position as a free variable. So Y is a free variable because when we put this system in row echelon form, that variable doesn't occur in a pivot. And it turns out if that variable doesn't occur in a pivot, then that variable is free to be anything. It can be any value. So they'll often say, like in WebAssign, they'll say if you have a free variable, start out by naming the first free variable t. So we're going to say y can be any number. Instead of y having to be exactly 5 and x being 3, let's say y can be any number t. In calculus or trig, sometimes we ran across instances where we had an infinite number of solutions and we would use n to represent any random number. So since y is free, y can be any number, and then if we back substitute x plus that any number equals 5, so in terms of our solution set, x, if we subtract t from both sides, x would be 5 minus t. So if we write that as an ordered pair, x would be 5 minus t, y would be t. So if you wanted to look at an example of a solution, then pick a random number to be t. Let's suppose we let t be 4. So when t is 4, x is 5 minus 4, y is 4. So that's an example of an ordered pair that works. If we think back to our original problem, isn't 1 plus 4 5? Isn't minus 1 minus 4 negative 5? If we let x be another number, for example, or t, I'm sorry, be another number, if we put a 5 in, then that would make x 0, y 5. So basically, by describing x and y this way, this just sets up a relationship. Since there's not one particular point that works, since there's an infinite number of points that works, this just describes the relationship between x and y. Whatever y is, x is 5 minus that number. And again, the way we set that up is when we put our system in row echelon form, y was a free variable, meaning that we didn't have y as a pivot. All right. Let me quickly. I think that's in general what 1.1 deals with. It deals with putting things in row echelon form by doing Gauss elimination. So again, in Gauss elimination, we want, after we have under our first pivot, we want all zeros. So basically no x of 1's in any of the other equations. Then whatever our next pivot is, we want all zeros underneath it. Whatever our next pivot is, we want zeros underneath it. So we begin by getting zeros under that one. Well, actually, I guess you would say you would begin by making that coefficient a 1 and then getting zeros. Then we would make that coefficient a 1 and getting everything 0 underneath it. Make that one a 1 and get all zeros under it. So we're just working our way across, getting zeros under each of our pivots. Now, we don't have time to work one example of every possible outcome, so that's kind of what the homework is for. This is the process. Now, as you work through homework, you might have something a little different occur. You might have one where you don't have a pivot in the second column. So if you don't have a pivot in your second column, that would make that variable a free variable. So when they ask you to describe your solution set, instead of being a specific number, that variable could be any possible number. Now in the second section, we're basically doing the same thing, except we're going to try to make it look a little prettier. Notice with all these x of 1's, x of 2's, x of 3's, after a while that almost looks like a jumbled mess. So if we could cut all of those x of 1, x of 2's, x of 3's out of this business and just have the coefficients, this would be a little less messy. So let's just take that system of equations and let's form a matrix out of that. Now, we're going to form what's called an augmented matrix. In an augmented matrix, it includes the coefficients on the left and your number on the right. Just a coefficient matrix, let's, I guess, illustrate the difference between a coefficient matrix and an augmented matrix. A coefficient matrix would be a matrix that is made up of just the coefficients on the left side. So 1, 1, negative 2 in the first row, 3, negative 2, 4 in the second row, 2, negative 3, 6 in the third row. Where an augmented matrix has all of that, but it also has another column in there. It has your solution column. Now some books come in and put numbers on your right side, those are your solutions. Just from what I've seen so far, this book really doesn't do that. It leaves the colons out, and it just tells you, hey, this is an augmented matrix, so these are the coefficients of x1, these are the coefficients of x2, these are the coefficients of x sub 3, and then these are your numbers. So let's take that augmented matrix and let's reduce it. Now we've already reduced this system using entire equations, having x1, x2, and x3 in there. But let's put this in row echelon form as an augmented matrix. So we already have a 1 in our pivot, so we want to get zeros underneath. So if we take 3 times that first row, and actually negative 3, negative 3 times 1 is negative 3, plus 3 would be 0. So our second row is going to be negative 3 times the first row, plus the second row. Our third row, to get a 0 here, we would need to add that to negative 2. So the easiest way to get a negative 2 is to do negative 2 times the first row and add it to it. So we're leaving the top row just like it is. And then the second row, we're going to do negative 3 times the first row and add that to the second row. So negative 3 times 1 plus 3 is 0. Negative 3 times 1 plus negative 2. Negative 3 times negative 2 plus 4. Negative 3 times 3 plus 1. So negative 3 times the first row plus the second row. Then we're doing negative 2. You see where the done is? Then to get a 0 here, we need to add that to negative 2. So negative 2 times 1 on top plus 2. Do negative 2 times the next column. So negative 2 times 1 plus negative 3. Negative 2 times negative 2 plus 6. Negative 2 times 3 plus 8. So that was negative 2 times the first row and then added to the third row. So we did that for each column. So real quickly, that's 1, 1, negative 2, 3. And that's 0, negative 5, 10, negative 8, 0, negative 5, 10, 2. So notice that got us all zeros there. So now that we have zeros under that first pivot, this is our second pivot. So let's make that a 1. And earlier we said, well, if we divide that by itself, that would make 1. So another way of saying that is to take the second row times negative 1/5 to give us our new second row. So the first row, we're not doing anything to it. The second row, we're multiplying times negative 1/5, so that gives us 1, negative 2, 8/5. And the the bottom row, for now, we're leaving the same. So now that we have a pivot with zeros underneath it, then our next pivot is a 1. We need a 0 underneath it. So what can we add to negative 5 to make 0? Ty, very good, Ty. You get a cookie. An imaginary cookie. Here you go. So to get a 0 here, we want to add 5 to that, so the easiest way to get a 5 is to multiply that times 5. So we're going to do 5 times row 2 to add that to row 3, and that'll give us our new row 3. So our first row, not doing anything to it. Our second row, not doing anything to it. Our third row, our new third row, will come from doing 5 times our row 2. So 5 times 0 is 0, plus 0. Then we'll come to the next column. 5 times that is 5, plus row 3. Then come to the next column. 5 times that, plus row 3. Then our last column, 5 times that, plus row 3. So if we do that, we get 1, 1, negative 2, 3. 0, 1, negative 2, 8 fifths. 0, 0, 0, 10. So keep in mind, the first column is the coefficient of x1s, the second column coefficient of x2s, the third column coefficient of x of 3s, and then these all we equal. So notice basically if we get a number here, zeros here, that is equivalent to the equation nothing equals 10. Which is what we came up with earlier when we saw the same system, and we said that means what? No solution. So that particular problem has no solution still, but notice that was a little less cumbersome not having to deal with all those letters and stuff in there. So now that we've used a matrix, let's go back and discuss the matrix a little bit. So we said this already, but hopefully you know that going horizontal, those are called rows. Up and down, vertical, those are called columns. So rows and columns. So if we're asked for the dimension or the size of a matrix, we describe it as its row by column. So how many rows does this matrix have? It has 2 rows. How many columns? 3 columns. So that's a 2 by 3 matrix. So that matrix, row by column, that's 3 rows. How many columns? 1 column. I always remembered it like a RC code. So RC or radio control. RC, so you describe the row first and then the columns. So if we have this particular matrix and we want to refer to a specific component of that matrix, let's say that's matrix A, then if we say A 2, 1, this means the component out of matrix A that's in the second row, first column. So which component of that matrix is in the second row, first column? 3. This is the second row. This is the first column, so 3. So in general, this is first row, first column. This is first row, second column. Second row, first column. Second row, second column. So just in case we run across that notation in the future, you'll know what that stands for. Alright, we've already talked about elementary row operations. We've talked about using those to put it in row echelon form. So then they do get into describing, well, what do we mean by row echelon form? So technically to be in row echelon form, it has to have there are 3 properties. If you have any rows that are all zeros, then you'll put those at the bottom. So if we add 2 rows together and they cancel and give us just all zeros, then we would put that at the bottom. Yeah, so this is row echelon. So for all non-zero rows, the first non-zero entry in a row is 0. So basically the pivot in each row, I said 0. So the first non-zero number is a 0. So the first non-zero number in a row is a 1. So if I have a row that's got some zeros in it, the first 2 coefficients are 0, and then we've got a number, that next number has to be a 1, if that's a non-zero number. So for example, that is not quite, and that fails the second property because the first non-zero entry is not a 1. So to put that in row echelon, we could take half of that second row to get our new second row. one doesn't have any rows that are all zeros, so we don't have to worry about putting them at the bottom. And then the first, this is a non-zero, so it's a 1. This is the first non-zero number in that row, so it's a 1.
But like on the last one we did, okay, the last equation we had was 0 equals 10. So are we just talking about like the left side of the equation?
Technically, for that to be in row echelon, we would have to divide that bottom row by 10. We would end up with the same answer because we would have a 0 on one side, a 1 on the other side, which is still not a true statement. But technically, for that to be in row echelon, you're right. We would want to multiply that by 1/10 or divide by 10. So those are the first two properties. The third one, they say this kind of wordy saying this. I'm going to read this and then may see if we can put this in simpler terms. They say for two successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. So the leading one in a lower row is farther right than all leading ones above it. Basically, as you go down, the farther you go down, the farther to the right your pivot is. Your leading coefficient in each successive row has to be farther to the right than in the previous row. So we can go back and look. Where was that already? So for example, let's look here. We could have very easily have made that a 1. Multiply that row by -1/5. But if we made that a pivot, is that farther to the right than the pivot above it? No, it's in the same position. Notice that one is farther to the right than that one. But to be in row echelon, the next pivot would have to be farther to the right than that one. So the next pivot can't be there. That's why we put a 0 in that spot. Going from the first to the second row, since the pivot was here, we can't have it there again, so we needed that to be 0. That's why we ended up with a 1 there and not there. So each successive row, basically, the leading coefficient is farther to the right than any previous row. So if we look at some examples, is that in row echelon form? What about that? Which row makes that not in row echelon form? coefficient is not farther to the right than the row above it. Is that a row echelon? Yes. Yeah. It doesn't say how much farther to the right it has to be. As long as each successive pivot is farther to the right. So our first pivot is in the first column. The next one is farther to the right. The next one actually skips a column, but as long as each successive pivot is farther to the right than the one above it, then we're good. Is that a row echelon? No. That one's not. Now we could easily convert that to row echelon. Right, which rows? The first and the last. If we take the third row, move it up top, leave the second row, move the top row down to the bottom, that would be in row echelon. Each pivot is a 1. Each successive pivot is farther to the right than the one above it. So yeah, that is row echelon. Let's make an addendum to that. So that's row echelon. Reduced row echelon has all of those characteristics, and also every column that has the 1 as a pivot has zeros everywhere else. So to be in reduced row echelon, if you have a column that has a pivot in it, then all other values in that column will be 0. So in words, that might sound a little confusing. But that's reduced row echelon. The first column has a pivot. Everywhere else is 0. The second column has a pivot. Every other value in that column is a 0. The third row has a pivot. Every other value in that column is 0. Now notice the beauty of reduced row echelon. If we look here, that top equation, if that's an augmented matrix, that top equation you have 1x of 1, no x of 2's, no x of 3's equals 3. That bottom equation you have no x of 1's, 1x of 2, no x of 3's equals 2. The bottom equation, no x of 1's, no x of 2's, 1x of 3 equals 4. So in reduced row echelon form, you don't even have to back substitute. In reduced row echelon, you basically read your solution straight off. Remembering that this is your solution column for the right side of your equation. And these are the coefficients of x1, x2, And I'm fine with us putting them on there. I'm not really sure why this particular book doesn't put them on there. The book that I learned out of used them, and I've seen I think some other books that used them. But you are right. Not putting the colons in there does make that a little more confusing. So if y'all want to do that, then I'm fine with that. We'll put colons all the time. So the only so we did Gauss elimination in the last section. To get in reduced row echelon, that's called Gauss-Jordan elimination. So let's see. Let's take one. And put in reduced row echelon. And in the book, they don't put the colons in, but that is augmented, so let's put it in there. So let's put this in reduced row echelon. So first of all, let's put it in row echelon. So we want a 1 in the first pivot, so we could get it more than one way. But what would be the easiest way to get a 1 in the first pivot? Swap 1 and 2. So let's begin by swapping row 1 and row 2. So 1, negative 1, 1, 0 for the first row, 2, 1, negative 1, 3 for the second, 0, 1, 2, 1 for the third. All right. So we have a pivot there. We need all zeros underneath it. So if we have a 2 here, then we want a negative 2 to go with that. So the easiest way is to do negative 2 times the first row plus the second row. That'll give us our new second row. Now, do we have to do anything to the third row to get a 0 in the first column? No. So the first row, we have the right pivot. We do negative 2 times that first one plus the second row, we get a 0. Negative 2 times that is 2, plus the second row is 3. Negative 2 times that is negative 2, plus the second row. Negative 2 minus 1 is negative 3. Negative 2 times that is 0, plus the second row is 3. We didn't do anything to the third row in this step, so actually a couple ways we could get a 1 as a pivot in the second column. We could swap them. We can also reduce that second row, either way. So that we end up with smaller numbers, let's multiply that second row by 1/3. So that's going to give us our pivot there in the second row as a 1. Because row echelon, we have to have 1s in our pivot positions. So if we do each of those by 1/3, we get a 0. 3 times 1/3 is 1, then -1, then 1. So now that gives us a pivot with zeros underneath it in the first column, a pivot of 1 in the second column, and we need a 0 underneath it. So if that is 1, what do you add to 1 to get 0? -1. So we want to take -1 times row 2, add that to row 3 to get our new row 3. Generally speaking, whatever row we're changing, like in this case we're changing row 3, generally speaking we're not going to multiply that row by anything. Notice we multiplied row 2 by something and then added it to row 3 to get our new row 3. Previously, we were changing row 2. In this step, we were changing row 2, so we didn't multiply row 2 by anything, we multiplied row 1. Alright, so if we do this, 1, -1, 1, 0, 0, 1, -1, 1. So if we do the opposite of row 2 plus row 3, we get 0 plus 0. We get -1 plus 1. -1 times -1, that's a +1 plus 2, so 3. -1 times 1, that's -1 plus 1, 0. So the opposite of row 2 plus row 3. Okay, so now what do we need to do to get that? We got one more thing to get that in row echelon. So what's the last thing to get that in row echelon? Yeah, we got to turn that 3 into a 1. So we can just do 1/3 of row 3 and make that happen. So if we take that bottom row times 1/3, we get a 1 there. Everything else is 0, 0 times 2. So that's row echelon. Now, reduced row echelon, once we get it in row echelon, then we need all of the values above our pivots to be 0. So that's a pivot. We have all the other values in that column 0. That's a pivot. We have a 0 here. We need one above it. That's a pivot. We need the other ones zeros. So usually when we start at the bottom, or start on the right side and say, well, let's get zeros in those. So if we want to get a 0 here, can't we just add those two together? So our second row is going to be from adding 1. So we're going to do the 1 at the bottom. So we're going to do minus 1 row 3. Minus 1 row 3 plus row 1. So the bottom row didn't change. So our new second row came from adding our old second and third rows together. So if we add these two together, we get 0 plus 0, 1 plus 0, negative 1. 1 plus 0 is not 0, which is negative 1 plus 1, and then 1 plus 0. To get our new first row, we do the opposite of the third row with the first row. So the opposite of 0 plus 1, the opposite of 0 plus negative 1, the opposite of 1 plus 1, the opposite of 0 plus 0. So we're about out of time. So the last thing we need a 0 there. So we can't combine that with the third row because you can't add 0 to something and make it go away. So if that's a negative 1, what did you add the negative 1 to make it go away? A 1. So notice there's a 1 right underneath it. So if we take row 2 and add to row 1, that'll give us our new row 1. So add the first two rows together, we get 1, 0, 0, 1. So that tells us that 1x1 equals 1. 1x2 equals 1. X of 3 equals what? X of 3 is 0. So basically the order triple 1, 1, 0 is a solution to that system of equations. Now that gets through about 90% of that second section, so I might throw together a little short video talking about one last thing in that second section, and then just kind of briefly describing the homework problems out of section 3. I didn't put many problems out of section 3. It's just a couple of applications. Basically applications of systems of equations. So I might work a couple of those, put a short video of that on Canvas, but then these homework problems are already available on the website. Any questions?